This video demonstrates the design procedure of a one-way RCC slab as per IS 456-2000 code provisions. Watch this video till the end to understand the basic concept of one-way slab and its design procedure in simplified manner. In this video, we will learn the design of a simply supported RCC slab for an office room floor having following data. The clear dimension of the room is 4 meter by 10 meter. The slab is supported by brick wall of thickness 230 mm on all four sides. The live load acting on the slab is 4 kN per meter square. The grade of concrete is M20 and the grade of steel is Fe415. The value of FCK for M20 grade concrete is 20 Newton per mm square and the value of Fy for Fe415 steel is 415 Newton per mm square. First of all, let us decide whether the slab is one-way or two-way. This slab is supported on all four sides. Hence, as per clause 9.3.1 of SP 34/1987, when a slab is supported on all four sides, then the slab is one-way if the effective length of the slab exceeds 2 times its effective width. To simplify this, we can say that when the ratio of long span to short span is more than 2, then slab will be treated as one-way slab. We have longer span as 10 meter and shorter span as 4 meter. The ratio of longer span to the shorter span is equal to 2.5, which is more than 2. Hence, this slab will be treated as one-way slab. In one-way slab, the shorter span is always considered for the design purpose, and a strip of 1 meter width is considered for the design calculations. Let us start with step 1 by deciding the initial thickness or depth of slab. One-way slab is generally designed as beam of unit width. Hence, for a given type of support condition, basic values of the span to depth ratio applicable for beams in IS 456 is also valid for slabs. Since the percentage of reinforcement in slabs is generally low in the range of 0.3 to 0.5%, a span to depth ratio of 25 to 30 is more appropriate by considering the modification factor for Fe415 steel. For this numerical, let us assume the value of span to depth ratio as 25. Rearranging the equation and putting the value of shorter span 4 meter, we get the initial effective depth or thickness as 160 mm. In slab, the minimum cover to the reinforcement shall not be less than 15 mm. Hence, assume a nominal clear cover by referring to table 16 of IS 456 as 20 mm and bar diameter as 10 mm. Calculate the effective cover by adding the clear cover and half the bar diameter. Thus, we get the effective cover as 25 mm. Now, compute the total depth or thickness of the slab by adding an effective cover to the effective depth, which comes to 185 mm. Assume the width of the slab strip equal to 1000 mm. In step 2, let us calculate the effective span of the slab by referring to clause 22.2 of IS 456 as clear span plus the effective depth of the beam or center to center of support, whichever is less. Hence, let us calculate first clear span plus the effective depth of the slab, which comes to 4.16 meter, and second center to center of support, which is 4.23 meter. Adopt effective span equal to least value between first and second, which is 4.16 meter. In step 3, let us calculate the loads acting on the slab. First, calculate the self-weight or dead load of a slab by multiplying the cross-sectional area of a slab with concrete density. Consider the slab width equal to 1 meter. After putting the values of slab thickness, slab width and concrete density, we get dead load of a slab as 4.625 kN per meter. Next, compute the self weight of the floor finish of the slab by multiplying the floor finish intensity with slab width. Here, we get it equal to 1.5 kN per meter. Now, calculate the total dead load by adding dead load of slab and dead load of floor finish. This is equal to 6.125 kN per meter. Next, compute the live or imposed load on the slab by multiplying the live load intensity with slab width. Here, we get it equal to 4 kN per meter. After getting dead load and imposed load, compute the total design or factored load per unit length using a load combination of dead load plus imposed load with a partial safety factor of 1.5 as given in table 18 of IS 456. Thus, the total design or factored load per unit length equals to 1.5 times dead load plus 1.5 times imposed load. This is equal to 15.19 kN per meter. This way, we get the analytical model of simply supported slab as shown in figure 1 to calculate bending moment and shear force. In step 4, we will do the computation of the ultimate bending moment and ultimate shear force due to design load. We will also calculate the limiting ultimate moment of resistance of the initially assumed cross section of the slab. Let us compute the ultimate bending moment mu first. The maximum bending moment for the simply supported slab is WL square by 8 at midspan. By putting the values of the design load and span, we get mu is equals to 32.86 kN meter. Next, compute the ultimate shear force Vu, which is equal to WL by 2. We get Vu equals to 31.6 kN. Finally, to check the adequacy of the assumed thickness of the slab, compute the ultimate limiting moment of resistance. Based on the clause 38.1 and annexure G of IS 456 for Fe415 grade steel, the moment of resistance is equal to 0.138 FCK BD square. By putting all the values, we get the moment of resistance equal to 70.65 kN meter, which is more than the acting bending moment of 32.86 kN meter. Hence, the initial assumed thickness of the slab is adequate and safe, and the section is under reinforced. After knowing the adequacy of the thickness of slab, let us compute reinforcement on the tension side of the slab in step number 5. The area of a steel required for the design bending moment can be calculated by referring the formula given in clause G1.1b annexure G of IS 456-2000. This formula results in quadratic equation. So, you need to solve the quadratic equation to get the value of AST. Otherwise, you can also use the simplified equation number 2 to calculate area of a steel. Let us use equation number 2 to compute the required area of a steel. By putting all the required values in the equation, the area of a steel required on the tension side is equal to 618 mm square. Now, let us check the minimum area of a steel required as per IS code. As per clause 26.5.2.1 of IS 456, the minimum area of a steel required for Fe415 steel is 0.12% of cross-sectional area of a slab. After computation, we get the minimum area of a steel in slab equal to 222 mm square, which is less than the required area of a steel. Hence, Required area of a steel on the tension side is equal to 618 mm square. Let us fix the diameter and spacing of bars to be provided as tension reinforcement. The minimum bar diameter of the main bar in the slab is 8 mm for Fe415 steel, and the maximum diameter of the bar is 1/8 of the slab thickness. So select the bar diameter as 10 mm. The cross-sectional area of this bar is 78.5 mm square. Now compute the spacing of bars by considering 1 meter width of a slab. Here we get the spacing equal to 127 mm. But as per the clause 26.3.3, the maximum spacing of the bar is 3 times the effective depth of the slab, or 300 mm, whichever is smaller. So let us calculate the second value of a spacing equal to 3 times effective depth, which is equal to 480 mm, and the third value of a spacing is equal to 300 mm. Now maximum spacing is equal to the minimum value of the first, second and the third value of the spacing. This is equal to 127 mm. Adopt the spacing of the bar as 125 mm. Provide 10 mm dia bar at 125 mm center to center along the span with alternate bars bent up at support. Thus, the total area of the main steel provided is equal to 628 mm square. In step 6, let us compute the distribution reinforcement which is provided against the shrinkage and temperature stresses. The required area of a distribution reinforcement is equal to minimum reinforcement as per the clause 26.5.2.1. So here required distribution reinforcement is equal to 222 mm square. Let us fix the diameter and spacing of distribution reinforcement. The minimum bar diameter of the distribution bars in the slab is 6 mm. So select the bar diameter as 8 mm. The cross-sectional area of this bar is 50.24 mm square. Now compute the spacing of bars by considering 1 meter width of the slab. Here we get the spacing equal to 226 mm. But as per the clause 26.3.3, the maximum spacing of the distribution bar is 5 times the effective depth of the slab, or 450 mm, whichever is smaller. So let us calculate the second value of the spacing equal to 5 times effective depth, which is equal to 800 mm. And the third value of spacing is equal to 450 mm. Now maximum spacing is equal to the minimum value of the first, second and third value of the spacing. Adopt the spacing of the bar as 200 mm. Provide 8 mm dia bar at 200 mm center to center perpendicular to the span. Thus, the total area of the distribution steel provided is equal to 251 mm square. Now, let us try to understand the reinforcement bar arrangement in 3-dimension figure. Here, the main reinforcement is provided as 10 mm dia at spacing 125 mm center to center along shorter span with the alternate bars are bent up at support. Straight bars are provided between 2 consecutive bent up bars. Hence, the spacing of 125 mm center to center is spacing at midspan of all the bars, including bent up and straight bars as shown in figure. At support, at bottom, only straight bars are available as the 50% bars are cranked up with the spacing of a 250 mm between the 2 consecutive straight bars. This means only 50% of the main steel is available at support at bottom. The distribution bars are straight bars provided perpendicular to main reinforcement bars as shown in figure. In step 7, check the feasibility of the slab section and reinforcement for the shear stress. The nominal shear stress due to shear force is obtained by using the equation given in clause 40.1 of IS 456. Putting the values of shear force, width and effective depth of the slab, we get shear stress equal to 0.197 Newton per mm square. Now let us compare this shear stress with the design shear strength of the slab. We can get this design shear strength based on the percentage area of a steel provided and the grade of concrete from table 19 of IS 456. So let us calculate the percentage area of the steel provided. In this, the value of AST is the area of a main steel provided at support at bottom, which is equal to 314 mm square. By providing the values of AST, width and depth of slab, we get the percentage of a steel PT as 0.196%. In table 19, the percentage value PT is lying between 0.15 and 0.25. Hence, the value of a tau C is also between corresponding values of 0.28 and 0.36 for M20 grade of concrete. Here, we can calculate the tau C by using linear interpolation formula. Let us mark the values of x1, y1, x2, y2, x and y. By putting all these values in the interpolation formula, we get y equal to 0.317, which is the value of tau C. As per clause 40.2.1.1 for slab, the design shear strength is equal to tau C into K, where K is based on overall depth of slab. This slab is 185 mm thick. Hence, the value of K is 1.3. After multiplying tau C with K, the shear strength is equal to 0.41 Newton per mm square, which is more than shear stress. Therefore, this slab is safe in shear. In general, slabs are always safe in shear. Finally, let us summarize the design and the reinforcement detailing. A simply supported one-way slab is designed with M20 grade of concrete and Fe415 steel. The thickness of slab is 185 mm. 10 mm diameter bars at 125 mm center to center are provided along the span with alternate bars bent up at support, while 8 mm diameter bars at 200 mm center to center are provided as a distribution bars perpendicular to the span. If you like this video, then share your thoughts in comment section, subscribe this channel and press the bell icon to get the notification of such interesting videos for visual and simplified learning of various civil engineering topics.